guys, hope you're ready to review fluids a little bit, because that's sort of what we're going to be doing in this video. It's going to be two videos. The first one is just kind of the conceptual review, and that's what the final's sort of based on, or is supposed to be, preparing you for that test anyway. The second video is me working MCAT-style problems in fluids. For those of you that are taking standardized tests and want to see that, that's up to you. You can use that resource. Okay, so fluids. What are the key points of fluids here? So the first is that pressure inside of a static fluid increases with depth. So we have rho GD, pressure is equal to rho GD, plus whatever pressure is on top of the fluid. This equation highlights the difference between something called gauge pressure and absolute pressure. Absolute pressure is this whole thing. Gauge pressure is just this first term. It's whatever the pressure is minus the atmosphere. And remember that P naught, for all the problems we work in physics, is 1 atmosphere. So take care of pressure increasing with depth in a fluid. Next thing that's on my mind is buoyancy. You remember that the buoyant force is equal to the density of the displaced fluid times the volume of the displaced fluid multiplied by gravity. So notice that the properties of the object that's either floating or sinking have nothing to do with the buoyant force. The buoyant force is strictly determined by the properties of the fluid itself. So, for example, let's say that I have two balls, ball A and ball B, and let's say they're the same mass. I'll just make it easier on myself. We might ask which one experiences the bigger buoyant force. Well, ball B displaces more fluid, so ball B has more buoyant force, we would say. Now, if an object is floating, then we know that it's neither sinking in the water or floating above the water, so the forces of weight and buoyancy are balanced. So if you're floating, we say that FB is equal to mg. And sometimes this lets us take shortcuts when we're solving problems. So, for example, again, we can come up with that same scenario here where we have ball A, ball B. Let's make ball B a lot bigger here. So ball B is larger now. Again, same mass. And we might ask how force of buoyancy on A compares to the force of buoyancy on B. And because they're floating, the buoyant force is providing just as much force to either object. And so we would actually put an equal sign in between those two. Okay. So much for buoyancy. We know that an object will sink if the buoyant force is less than the weight. And a way you can check that is you can set the volume of the fluid equal to the full volume of the object. That is, you can calculate what the buoyant force would be when the whole object is submerged underwater. And if it's still smaller than the weight, it's going to sink. So the other thing we should say is buoyant force acts up. So this is why a candle flame in free fall doesn't go upwards, it goes out in all directions. Buoyant force acts against the gravitational field. And if there is no gravitational field, buoyancy isn't really a thing. So, okay. Alright, so that's buoyancy. What else do we need to cover? So there's Pascal's principle. Pascal's principle says that a change in pressure is transferred undiminished, is the fancy terms, throughout the fluid. So the example that we usually give of this is a hydraulic press. Let's say I have a platform here and a platform here, and one is 4 times bigger than the other in area, whatever, and they're both floating in fluid. Okay, and let's pretend that these platforms seal off the container so there's no atmosphere that can get into that fluid. If I put, let's say, 30 pascals down on that first platform, that change in pressure is transferred undiminished throughout the whole fluid. So that 30 pascals is going to come back over here, and there's going to be a change in pressure of 30 pascals here. So there's going to be an upwards 30 pascals over here. Okay. So that's Pascal's principle. It's the way by which hydraulics work. Well, it's actually the way the brake in your car works. You apply just a little bit of force, and that propagates throughout the entire fluid. Sometimes it's stated as a fun formula, F1 over A1 is equal to F2 over A2, and notice that's just saying that P1 is equal to P2 because pressure is literally force over area. So that's Pascal's principle. Okay, what else in the fluid statics regime? I think that's all except for a couple of key points. One is when you're static, fluid seeks its own level. Which we kind of already know. Water will, if it's poured into a canyon, it's going to explore all the cracks and crevices in the canyon before rising along the canyon wall. It's for fluid statics. Another corollary of that is that all points connected by horizontal lines have the same pressure. So the example that you've seen me exploit of that is that if you have, say, I don't know, I'm going to make it up here. Here's the ground. And I have this, like, these crazy chambers here in the ground here. And the question is if these two, points A and points B, are at the same elevation, they will have the same pressure, regardless of how much fluid appears to be on top of either. Because water seeks its own level, this is kind of a nice property. The pressure at B is equal to the pressure at A. So you might see some problems that have to do with that idea. That's pretty much all I can think of in the fluid statics regime. Let's quickly move over to the fluid dynamics, which seems a lot harder, but there's actually fewer principles that are applying in that case. So here's the fluid statics idea here. Oh, sorry, fluid dynamics. Dynamics. So, fluid dynamics, the first thing we're going to talk about is the continuity equation. That's the one that says A1V1 is equal to A2V2, which is kind of an important idea. That basically just says that if I have a pipe and it gets narrower, the throughput Q has to be the same in both regions of the pipe. Otherwise, water would bunch up in the pipe, and that just doesn't happen. Water is incompressible for our class. So, what that means is that the smaller the pipe, the faster the fluid velocity. So something that goes along with this is Bernoulli's principle. Usually these are connected in problems. Bernoulli's principle just says that faster fluid velocity equals lower pressure. And so that's a little bit counterintuitive. We're used to thinking of fast-moving fluid as being higher pressure, but remember that it's the opposite of what you think it is. If fluid is moving faster in the small region of pipe, that means that the pressure here must be tremendous, and that this must be relatively smaller in order for us to get an acceleration from V1 to V2. So it's kind of the way I think about it. Bernoulli's principle leads into a kind of an energy conservation equation that we call Bernoulli's equation. So we say that P1 plus the kinetic energy of the fluid plus the potential energy of the fluid is equal to the same thing in another region of pipe. That's a conserved quantity there, the total energy of the fluid. And so we can sometimes use this to solve some complicated pipe problems. On the final itself, I'm not going to have you use this to solve one of those weird, crazy problems that we did on test 1, but I do expect you to understand the general principles at play. That is that if I have a pipe and it gets smaller, I do expect to have the fluid velocity increase. Now in the human body, that's not the case. The aorta has a much higher fluid velocity than the capillaries, and there's two effects that are going into that. The first is that viscosity is a thing. The smaller the pipes become, or the tubing or whatever it is, the greater the friction, if you like, of that fluid with the walls of the container that it's moving through. And so that affects things. The other thing is that there's so many more capillaries than there are. Um, if you add up all the area, all the cross-sectional area of all the capillaries, and you compare that with the aorta, the capillaries actually win by orders of magnitude, which is another reason why fluid moves slower in the capillaries. And the final reason is that blood is different than water. Blood is a double fluid system. It means there's two components at least to blood from a hemodynamic standpoint. There's the plasma, and then there's the blood cells. And on very, very small scales, the fact that you have two things actually becomes important in dictating how the dynamics of that fluid works. So this is why there's kind of a disparity when we say the smaller you get the aperture size, the faster the fluid goes. That works for classic fluids where viscosity isn't acting, and you're not dealing with these really tricky fluids that show up in biology. So anyway, so those are the essential concepts that are going to go into this portion of the test. So if you feel good about that, you're on solid ground. I'm going to now work some MCAT problems. You can stick around if you want to do that, or you can go do other things with your highly valuable life. So take care, okay? Bye.